There is a car on sale right now that does not have a battery inside it. Not because it runs on petrol, not because it is a hydrogen vehicle or some experimental concept sitting behind a rope at a technology exhibition. It is fully electric, it charges, it drives, it does everything an electric car is supposed to do. It just does not have a battery in the traditional sense of the word. Because in this car, the battery and the car are the same thing. The floor you sit on, the walls around you, the structure holding the entire vehicle together, all of it stores energy. All of it is the battery. And before you process that fully, here's the number that made an entire room of automotive engineers go very quiet in March 2025. 5 minutes, not to top up, not to add a few miles to limp to the next station. 5 minutes to add 250 miles of real driving range. 5 minutes from nearly empty to ready to drive across 3 counties. In the time it takes most people to order and collect a coffee, this car goes from almost dead to genuinely capable of taking you almost anywhere you need to go today. That is not a laboratory result. That is not a carefully staged demonstration under ideal conditions with an asterisk at the bottom of the slide. That is a production vehicle you can walk into a showroom and buy. The company that built it started 30 years ago in a single rented room making batteries for Nokia phones. That detail is not just interesting background. It is the entire explanation for how they were able to build something that every other car manufacturer on Earth is currently scrambling to understand. If you have ever sat at a charging station, watching the percentage climb slowly, while the car next to you at the petrol station fills up and drives away in 3 minutes, what you are about to hear is going to reframe that frustration entirely. We are going to walk through exactly how this technology works, why it represents a genuine shift rather than an incremental improvement, and what it actually means for the decision you make the next time you buy a car. Hit the like button right now if this is the kind of content you want more of. It takes 1 second and it directly helps this channel reach more people who care about where cars are actually going. Subscribe and turn on the notification bell. This story is just getting started. Let us get into it. To understand why what BYD built in 2025 is genuinely significant rather than just impressive marketing, you have to go back to where the company came from. Because the origin story is not decoration, it is the mechanism. Shenzhen, China. Wang Xuanfu is a chemist in his late 20s with a chemistry degree, roughly $300,000 in starting capital, and a clear observation about where an opportunity existed. Japanese manufacturers controlled the global market for rechargeable batteries and charged prices that reflected that control. Wang believed he could reverse engineer the process, produce domestically, and undercut them, not through cutting corners, through understanding the chemistry at a level deep enough to find efficiencies that the established players had never needed to look for because they had never faced serious competition. He was right, and the speed at which he was right surprised almost everyone watching. By 2000, BYD was the largest nickel-cadmium battery manufacturer in the world. 2 years after that, the top lithium-ion supplier globally, Nokia, Motorola, the companies whose phones were in hundreds of millions of pockets, were customers. The operation that had started in a rented room was now supplying the energy storage that made the mobile communication revolution possible at scale. But the significant thing about that decade of battery manufacturing was not the commercial success. It was the knowledge that accumulated alongside it. Wang and his engineers spent 10 years taking batteries apart, understanding every chemical reaction, mapping every failure mode, identifying every inefficiency in how energy was stored and released. They understood batteries not as components to be sourced and integrated, but as systems to be mastered from the molecular level upward. That understanding did not become less valuable when BYD entered the car business in the early 2000s. It became the entire foundation of everything that followed. Traditional car manufacturers think about batteries the way they think about seats or windscreens. It is a component with a specification. You find a supplier who meets the specification at the right price, you engineer the vehicle around it, and you move on to the next problem. BYD never had that relationship with battery technology because BYD was the battery technology. The car was always a vehicle for what they already knew how to do better than almost anyone else on Earth. That distinction sounds subtle. The results it produces are not subtle at all. By 2020, BYD made a bet that the rest of the industry considered either brave or misguided, depending on who you asked. They committed their future to a battery chemistry called lithium iron phosphate, a chemistry that most competitors had already decided to move past. The reason everyone else had moved on was straightforward. Lithium iron phosphate could not match the energy density of newer chemistries. It stored less energy per kilogram. In a market where range anxiety was the primary barrier to EV adoption, choosing a lower energy density chemistry looked like choosing to compete with one hand behind your back. BYD looked at the same data and reached a different conclusion. What lithium iron phosphate offered, that the chemistries replacing it did not, was natural thermal stability, meaning it did not want to catch fire the way other chemistries did under stress. It offered significantly longer cycle life, meaning it degraded more slowly over hundreds of charge and discharge cycles. And it offered lower raw material cost because it did not depend on cobalt, a material whose supply chain is both expensive and ethically complicated. The energy density problem was real, but BYD believed it was an engineering problem rather than a chemistry problem. And engineering problems can be solved if you understand the system deeply enough. Their solution was to redesign the cell geometry entirely. Instead of building battery cells in the conventional cylindrical or prismatic format and then stacking those cells into modules and those modules into packs, BYD created cells that were long and flat, shaped the way the name describes, like blades. These blade cells could be arranged directly into the pack without any intermediate module layer, which eliminated a significant amount of packaging material that had been taking up space without storing any energy. The result was a battery pack that used its available space dramatically more efficiently than the architecture it replaced. The energy density problem that had made lithium iron phosphate look like a dead end turned out to be partly an architecture problem rather than a chemistry problem. Change the architecture and the chemistry becomes competitive again. To demonstrate the safety advantage publicly, BYD ran a fully loaded 46-ton truck over a blade battery pack. The pack did not rupture, it did not catch fire, it barely deformed. Wang Chuanfu said directly that his goal was to remove the phrase spontaneous combustion from the electric vehicle conversation entirely. That is a specific kind of confidence, the kind that comes from having built something yourself and understood every part of it. The blade battery was a genuine achievement, but it was still fundamentally a box, a well-engineered box, a safer box, a more space-efficient box, but a box that went underneath the car and did one job. The next step was asking whether the box needed to exist at all. Every electric vehicle on sale today is built around the same fundamental layout. The battery pack sits underneath the passenger floor as a separate structural unit. It does its job, storing energy, and the rest of the car is engineered around it. The battery is furniture. The car is the room built to accommodate it. This layout creates a set of problems that every EV manufacturer is currently managing rather than solving. The battery pack adds mass that contributes nothing to the structural rigidity of the vehicle. A heavier car needs more energy to move itself, which means a larger battery to achieve the same range, which means more mass, which means more energy required. The cycle works against itself, and every manufacturer building EVs today is somewhere inside that loop trying to find the exit. The packaging around the battery, the protective casings, cooling systems, structural frames, and wiring channels that surround the cells consumes a significant proportion of the total space available. In a conventional pack design, a large fraction of the volume that could theoretically store energy is occupied by the infrastructure required to protect and manage the cells. The cells themselves are a minority of the total package. Cold weather attacks the chemistry directly. At low temperatures, the electrochemical reactions inside a lithium battery slow down. The battery loses accessible capacity. Charging speed drops because the cells cannot absorb current quickly when they are cold. The car has to spend energy keeping the battery warm enough to function, which reduces the range available for actual driving. Every EV owner in a cold climate knows this experience. The range estimate that looked reasonable at home looks increasingly optimistic as the temperature drops. Charging time is the most visible friction point because it is the comparison that gets made every time someone stands at a pump watching their tank fill in 4 minutes. The best public charging infrastructure available today adds meaningful range in 30 minutes on a good day. That is genuinely fast compared to what was available 5 years ago. It is genuinely slow compared to the alternative everyone grew up with. BYD looked at the complete list of these problems and decided that iterating on the existing architecture would not produce the results the market needed. The architecture itself had to change. The question they asked was one that sounds almost naive until you examine the engineering answer. What if the battery was not inside the car? What if the battery was the car? The technology they developed in response to that question is called cell-to-body integration. The principle is more elegant than it sounds, and the implications are more significant than almost any single announcement the automotive industry has produced in the past decade. In a cell-to-body system, the battery cells are not packaged into a separate unit and then mounted to the vehicle. The cells are structural members of the vehicle itself. The upper surface of the blade cell array forms the actual floor of the passenger cabin. The cells span between the structural elements of the body, distributing load the way a steel crossmember would. The battery is not underneath the car. The battery is part of what the car is made of. The analogy that makes this click is the difference between carrying a heavy bag and wearing a backpack versus having your skeleton do the load bearing directly. In the old design, the battery is the heavy bag, always along for the ride, always adding to the total weight without contributing to the structure. In the new design, the battery is part of the skeleton. It holds the car up, absorbs forces during cornering and impacts, and carries energy at the same time. The structural consequences of this change are measurable and significant. BYD's testing found that cell-to-body construction produced a vehicle body approximately 70% more rigid than their previous architecture. That level of structural stiffness puts the car in the same category as vehicles costing considerably more, vehicles that achieve similar rigidity through exotic materials and expensive manufacturing processes. BYD reached the same destination by changing where the battery lives. The efficiency consequences are equally significant. With the intermediate module layer eliminated and the protective packaging dramatically reduced, approximately 76% of the total system volume is now occupied by actual energy-storing cells. In conventional pack designs, that proportion is much lower because so much of the available space is consumed by everything surrounding the cells rather than the cells themselves. More cells in the same space means more energy stored. More energy stored means more range without adding weight. This is why BYD's newest models using this architecture post range figures above 600 miles. Not because they fitted a larger battery, because the battery they have is finally using almost all of its available volume for the job it is supposed to do. Then came March 2025, and the number that changed the conversation. BYD held a product event and presented the engineering behind their new charging system alongside the cell-to-body platform. The crowd followed the technical explanation with interest. Then the slide appeared showing the charging performance figure. 10% to 70% in 5 minutes. Using infrastructure delivering 1,500 kilowatts of power, roughly 40 times the output of a standard home charger. BYD demonstrated that their system could accept charge at a rate that made the 5-minute window genuinely meaningful rather than a marketing claim dressed up as a specification. In one of their flagship models, that 5-minute window delivers approximately 400 kilometers of range, around 250 miles. The charging time objection to electric vehicles has always rested on a specific comparison. A petrol station stop takes under 5 minutes. An EV charging stop takes meaningfully longer. That comparison is what BYD's system makes obsolete. When the charging stop is 5 minutes, the comparison no longer applies. The objection loses its foundation. The cold weather performance figure deserves specific attention because cold climate range and charging degradation has been one of the most persistent and legitimate criticisms of electric vehicle ownership in northern climates. At minus 30 degrees Celsius, which represents genuinely extreme winter conditions beyond what most people will encounter in daily life, BYD's system charges from 20% to 97% in approximately 3 minutes more than it takes at room temperature. 3 minutes. Not 3 times as long, 3 minutes longer. This is a fundamentally different relationship with winter than any current production EV offers. The thermal management built into the cell-to-body structure maintains the cells within their optimal operating range, even when the ambient temperature is pushing toward the limits of human comfort outdoors. The battery does not need to spend energy warming itself up before it can accept charge. It is already at the right temperature because the thermal management system is integrated into the structure rather than bolted on afterward. The vehicle carrying this technology in its most complete form is the Yangwang U7, BYD's flagship full-size luxury sedan. Under Chinese certification testing, it achieves a range figure exceeding 1,000 kilometers on a single charge. Real-world driving will produce lower figures because real-world driving always does. But even with conservative adjustment for real conditions, the range is in territory that makes the question of whether you will need to charge on a given journey largely academic. For most journeys, most people actually take. A battery that charges in 5 minutes is only transformative if there are places to charge at that speed. BYD understood that delivering this technology without the infrastructure to support it would produce exactly the kind of early adopter frustration that has held back previous technology transitions. They solved the infrastructure problem before the car went on sale. The challenge with 1,500 kilowatt charging is that drawing that power instantaneously from the grid at scale would create demand spikes that electrical infrastructure in most locations cannot handle. BYD's answer to this problem is built into the charging stations themselves. Each flash charging station incorporates its own energy storage system. Throughout the day, the station draws power from the grid slowly and steadily at a rate the local infrastructure handles without difficulty. That energy accumulates inside the station. When a car arrives, the station releases its stored energy at full speed directly into the vehicle battery without placing any sudden demand on the grid at all. The station does the work continuously throughout the day so that the car can do its work in 5 minutes. BYD had over 4,000 of these stations operational before the technology reached customers. Their target for the end of 2026 is 20,000 stations across China. This matters because the historical failure mode of new charging technology has been the circular problem where network operators will not invest in infrastructure until there are enough compatible vehicles to justify it, and consumers will not buy compatible vehicles until the infrastructure exists to support them. BYD eliminated that problem by building both sides of the equation simultaneously. The scale at which BYD operates gives this technology a momentum that is difficult to overstate. Last year, the company sold over 4 million vehicles across a range that spans from affordable city cars to high-performance luxury products. Cell-to-body integration is not a feature restricted to one flagship model at the top of the range. It is a platform, and platforms spread across product lines as the manufacturing process matures and costs fall. The physics that makes structural battery integration work in a sedan works equally well in a van, a truck, a bus, or stationary energy storage for buildings and power grids. The same fundamental insight that the structure and the energy storage can be the same physical thing applies across every application where you need to move weight efficiently or store energy compactly. Every manufacturer currently building or planning electric vehicles is looking at what BYD demonstrated in 2025 and calculating the distance between where they are and where they need to be. Some have structural battery programs in development. None has yet combined cell-to-body construction, 5-minute charging, meaningful cold weather performance, and a deployed charging network in a single production vehicle available for purchase. The benchmark moved. It moved considerably. And it moved in one announcement. So what does this mean practically for someone making a car purchase decision in the next year or two? It means the three objections that have accounted for the majority of hesitation around switching to electric vehicles have been addressed simultaneously by a single technology platform. Charging time was the most cited friction point. 5 minutes removes it, not as a future promise, as a current specification in a car you can buy. Range was the second. Over 600 miles in production models and over 1,000 miles in the flagship removes it. The question of whether you will run out before you reach your destination becomes largely theoretical for any journey a reasonable person plans to take. Cold weather was the third. 3 extra minutes of charging time at minus 30 degrees removes it. The experience of watching a charging station deliver power at a fraction of its rated speed on a freezing January morning becomes a story you tell about older technology rather than a problem you plan around. When all three objections disappear at the same time, the decision calculus changes fundamentally. Not incrementally, fundamentally. The structural benefits extend beyond the battery performance. A body that is 70% more rigid than the previous architecture handles with greater precision, communicates the road more clearly through the steering, and distributes the energy of a collision across a larger proportion of the vehicle structure. The battery being integral to the structure means it is protected by the structure rather than being a vulnerable element underneath it. There is also a longer-term cost trajectory worth paying attention to. Fewer components, less packaging material, more of the physical system dedicated to its primary function. As the manufacturing process for cell-to-body construction matures, the cost per vehicle comes down. Technologies that begin in flagship products at premium prices follow a consistent path into mainstream products at accessible prices. The 5-minute charging system that currently lives in a high-end luxury sedan has a clear route into vehicles that ordinary buyers make ordinary purchasing decisions about. The electric vehicle was always going to reach this point eventually. The point where the remaining practical objections to switching fell away and the decision became straightforward rather than a calculated compromise. The question was always which company would get there first and how quickly the rest of the industry would follow. In March 2025, BYD put a number on a screen in front of a room full of automotive professionals, and the room went quiet. 5 minutes, 250 miles. A company that started making phone batteries in a rented room just redefined what electric mobility means in practice. If this gave you something to think about, hit the like button before you go. 1 second of your time makes a genuine difference to whether this channel can keep producing content like this. Subscribe and turn on notifications so you catch the next one before it reaches the mainstream. And leave a comment with your honest answer. If there was a 5-minute flash charger near your home tomorrow, would that finally make the switch feel like an obvious decision rather than a compromise? I read everything. See you in the next one.